In this video, we're going to define horizontal asymptotes as well as slant asymptotes. Please keep in mind that asymptotes are guiding functions or guiding lines to the function. What we want to do, again, just like we did with holes and vertical asymptotes, is we want to be able to identify them without looking at a graph, but it's helpful for us to first graph a horizontal asymptote and a slant asymptote to better understand what they're supposed to look like, and then we'll be able to algebraically define how they're built. So a horizontal asymptote should appear as though, again, a horizontal line that the function doesn't cross. So for instance, this function right here could have a horizontal asymptote specifically sitting at this location. Let's call it y equals 2. You'll notice how the horizontal asymptote this time, instead of like the vertical asymptote deals with x equals, the horizontal asymptote deals with y equals. For a slant asymptote, a very similar situation occurs. The only difference, however, is that a slant asymptote occurs when it's going to not be a perfectly horizontal line, but a slight linear function with a slope to it. So this right here might be a slant asymptote. We're going to go ahead and just label that as y equals x as that slant asymptote. Now it's important to understand that the slant asymptote will replace the horizontal asymptote. It will only have either a horizontal asymptote or a slant asymptote. Now in some circumstances, in more complicated examples and more complicated classes, it is possible for a function to have two different horizontal asymptotes. One that specifically the function will do something like this. And again, these are very special cases. They're uncommon, but they can happen. So a case like this, you'll notice here that there's a horizontal asymptote in the negative direction, and there's a horizontal asymptote in the positive direction. We're going to go ahead and explain how you would describe this algebraically in another video, but for right now, the important part is that these are very rare cases, and they don't come up very often in algebra in our pre-calculus classes. These two cases, however, appear regularly. So it's important for us to be able to identify these functions, y equals 2 or y equals x for the horizontal or slant asymptotes, and it's also important for us to recognize that these things have to be identified algebraically, and then we have to be able to graph them. Also note that I could draw a vertical asymptote, say here, and say the graph could look something like this in the grand scheme of the problem in terms of how it's identified and graphed. So you'll notice here again that the vertical asymptote exists. There can be more than one vertical asymptote, but there will only ever be either one slant asymptote or one horizontal asymptote. These cases down here are extremely special cases where the algebra is a bit more complicated to deal with, and they don't appear very often in pre-calculus. So now that we have slant and horizontal asymptotes defined, the question is how do we algebraically identify what they are? So for instance, if we're looking at a function that looks like this, f of x equals 9x squared over 3x squared plus 1, versus this one here, f of x equals 9x over 3x squared plus 1, versus the last one, I'm going to go ahead and relabel this as g of x, the last one being h of x equals to 9x cubed over 3x squared plus 1. Now, if we're talking about what the function is doing, we have to talk about horizontally what the function is doing. Does it look like as we're approaching an x value of infinity that the graph is leveling off somewhere? That a value is increasing uncontrollably like this one is, or that it's decreasing uncontrollably similar to what this one is doing. So that's the concept of the way we want to get it across. If you look at this right here, the behavior of the function will boil down to the largest power of x in the problem. In this case, the largest power of x on top is x squared. The largest power on the bottom of x on the bottom is x squared as well. Those two details specifically correlate with the concept that the top is increasing at the exact same rate as the bottom is increasing. This goes for both negative and positive values. If I plug in a positive, very large positive x value on top and on bottom, that plus 1 is not going to affect the overall scheme of these two things. So the concept is when we're looking at a function to determine its horizontal asymptote, you're going to look at the largest powers of x. So over here off to the side, this is our rule for identifying or locating the horizontal asymptote. And that rule is going to revolve around the largest powers of x. So let's just say I have f of x is equal to a sub n x to the n, again, n, plus a bunch of other values all the way down to a sub 0. And then we have another polynomial in the denominator of this function. We're going to call it b sub m. Okay, x to the m plus, and then values until I get a sub 0. Now, it might be more beneficial for us to use different things to identify the n and the m, but we could just say, well, what's the top power? Okay, I'm going to say t is equal to the top power, the largest power on top, and then we're going to go ahead and use b for equals to the bottom power, the largest power on the bottom. With those two stipulations made, what we're going to do is we're going to say if the top power is smaller than that of the bottom power. So if this value up here, if the power right here on top is smaller than the value on here on the bottom, then the value on top is not going to get as large as fast as this one does. And if you think about it, constant term values, I'll say 1 over 10 versus, let's say, 10 over 1,000. Again, the values on the bottom are going to get larger so much faster than the values on top. If I do the next one, 100 divided by, this will be 1, 2, 3, 4, 5, 6, I think, if I drew that correctly. But you'll notice here that if you start typing these numbers into a calculator, that this value is going to get smaller and smaller and smaller, closer to 0. If this is the case, if you see the top power is smaller than the bottom power, then you have a horizontal asymptote, and y equals 0 is that horizontal asymptote. This can be proven using details in calculus, but since we don't have those skills in calculus yet, we kind of just make generalization rules about this, and those generalization rules will hold throughout all the algebra that we do. So the next stipulation is, what if the top power is equal to the bottom power? Well, that means that the values on top and bottom are simultaneously increasing at the exact same rate. If they're increasing at the exact same rate, very much similar to this, again, x squared divided by x squared, those powers aren't really going to matter in the grand scheme of the problem. All that's going to matter is the coefficients. So y equals a sub n over b sub m is your horizontal asymptote. To better show this with an example, this one right here, you'll notice the top power, largest top power is x squared, largest bottom power is x squared. Therefore, I have a horizontal asymptote, which I'll abbreviate HA, is y equals the 9 divided by the 3. This is my horizontal asymptote. And remember, the horizontal asymptote will always be defined as y equals, never x equals. The last case is, what if the top power is now larger than that of the bottom power? At this point, you'll have values on the top increasing so much more rapidly than the ones on the bottom, so these values basically switch, and you'll notice that it's going to be getting larger on top, and the bottom won't keep up to the point where it's going to approach infinity. If this approaches infinity, you don't have any horizontal asymptote. However, there exists a slant asymptote. And we're going to go ahead and talk about how we identify what that slant asymptote is, or how we can find out what that slant asymptote is later on. So, I've done the first one here where the power on top and the power on the bottom are exactly the same. I will simply use y equals the coefficients divided by each other. If I look to g of x, however, you'll notice that the power on the bottom is larger. And again, with the power on the bottom is larger, looking here, you're going to notice that I have the top is smaller than the bottom. Y equals 0 is my horizontal asymptote. So for every single one of these cases, there is a specific answer you're looking for. It's either I have y equals 0 as an answer, I have y equals a coefficient divided by a coefficient is an answer, or I have no horizontal asymptote, but there exists a slant that I still have to find. So this example right here, you're going to look at that and you're going to say, do I have a horizontal asymptote? And well, because the power on top is larger than the power on the bottom, again, we're looking at the largest power. So if this thing had some extra terms to it, say x squared and then minus 4, then it doesn't matter. This 9x cubed is still the largest power on top. We're still only going to look at that term compared to that term. And since the term on top has a larger power than the term on the bottom, there isn't going to be any horizontal asymptote, but there will be a slant asymptote that we're still going to have to find. Again, we'll go ahead and identify how you're going to find those in a separate video. So the concept here is, if you're looking for a horizontal or slant asymptote, you have to look to the powers of the numerator and the powers of the denominator, specifically the largest power. So if we look at one more example, I'm going to go ahead and label this one also as f of x. Let's go ahead and look at all the terms, say 3x to the 4th minus 7x to the 7th plus 2x to the 3rd minus 4, all divided by 8x to the 7th plus 2x to the 4th minus 7x squared plus 1. if we have a rational function that looks like this, now this is a really nasty rational function, and doing anything other than finding the horizontal asymptote would be very unlikely to be asked. But by looking at this, again, I'm looking for the largest power of x in the numerator. It's not the fourth, even though it looks like that's the first term. It happens to be this negative 7x to the 7th. And I'm going to go ahead and take that negative 7x to the 7th term out of there for a second so I can focus on it. On the bottom, you'll notice that the 7th power is actually the first power and is the largest. So I'm going to look at that 8x to the 7th as well. Now, if I'm looking at just those two pieces, again, this is probably poor notation to use, but being able to tear them out of there and looking at them separately is probably going to be a more efficient way than trying to keep track of everything that's going on here. Not to mention, this negative symbol has to carry with that negative 7. And since the powers on top and on bottom are the same, my rule is if the powers are the same, I have to take the coefficients and then divide them by each other. So for this problem, our horizontal asymptote will be y equals a negative 7 on top divided by 8 in the denominator. And again, those come from the coefficients, not from the powers. The powers tell me what I'm going to have. The coefficients, in this particular case, tell me what it is. If the powers, again, were slightly different, such that the top had a smaller value, then I'd look at y equals 0 as my horizontal asymptote. If the top had a larger value, then I wouldn't have any horizontal asymptote, but I would have a slant asymptote. So that's how you're going to define horizontal and slant asymptotes and how you're going to find them algebraically.